Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 27, Phi-Computation, Letting Reality Compute. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. We are deep in Book 10.5, Information Systems. We have learned to send and store phi patterns. Now, we ask them to work. We enter the computational foundry. This is not a room of silicon chips executing step-by-step instructions. It is a chamber where a physical phi system, a network of lasers, a lattice of superconducting qubits, a fluid of swirling vortices, is set up and then set free to evolve according to its own natural dynamics. Its final settled state is the answer to a problem we posed. Your new skill is that of the computational physicist. You are learning to map a difficult computational problem onto the physics of a phi system, to let that system find the solution through its own natural tendency to seek coherence, and to read the answer from its final pattern. This is not programming a computer to simulate physics. This is asking physics to compute. Scene: the computational foundry. The room thrums with a low, coherent hum. In the center, a crystal about the size of a sugar cube is held in a complex nest of wires and optics. This is a coherent Ising machine, a network of pulsed lasers whose phases represent spins. The problem, displayed on a console, is a max-cut problem on a 100-node graph. Color each node black or white to maximize the number of edges connecting different colors. It's a classic hard optimization problem. You don't see code, you see a mapping. Each graph node is mapped to a laser mode. Each edge's weight is mapped to a coupling strength between lasers. The machine's natural tendency is to settle into a phase configuration that minimizes a certain energy, which you have engineered to correspond to the negative of the cut value. So, minimizing its energy maximizes the cut. You press run. The lasers fire. Their phases, visualized as arrows on a screen, begin to twitch and search. They are not following an algorithm. They are following coupled differential equations, exploring a high-dimensional energy landscape. After a few microseconds, they lock. The arrows freeze, a stable pattern. You translate it back. Black, white, white, black. The console calculates the corresponding cut value and compares it to the best-known solution. The match is 99.7%. Our puzzle is one of translation and trust. How do we take a well-defined computational problem, often a minimization or constraint-satisfaction problem, and embed it into the initial conditions and couplings of a physical phi system such that the system's natural evolution towards coherence, energy minimum, finds a good, often optimal solution? And how do we verify that this natural computation is actually better than running an algorithm on a digital computer? The problem embedding skill. This part teaches a mapping and validation skill. It is the skill of reformulating a computational task into the language of phi constraints and energy landscapes so that a physical system's quest for coherence becomes a quest for the solution. Our core question about phi is, given a computational problem with a cost function to minimize or constraints to satisfy, can we construct a phi system with adjustable parameters whose effective energy function is isomorphic to that cost function such that the ground state, or a low energy state of the physical system, corresponds to a high-quality solution of the original problem? We are moving from using computers to simulate reality to using reality as a computer. The anchor image, the water finding its level. We will use the anchor image of water finding its level or a ball rolling downhill. A digital computer solving an optimization problem is like a surveyor with a map and a calculator, painstakingly testing points. An analog Phi computer is like releasing a ball on a physical model of the terrain and watching where it rolls. The ball doesn't calculate, it obeys gravity. It naturally seeks the low point. Our job is to sculpt the terrain, the energy landscape, so that the low point corresponds to the answer we want, and then to build a very sensitive ball and a way to see where it stops. The coherence selection principle in computation. In analog Phi computation, coherence is the driver of convergence. Constructive resonance, alignment, in computation means the system successfully finds a deep, low-energy valley, a coherent attractor, that represents a good solution. The many degrees of freedom, laser phases, spin directions, lock into a mutually consistent, stable pattern. Destructive resonance, dissonance, means the system gets stuck in a local minimum, a small pothole instead of the Grand Canyon, or fails to cohere at all, producing noisy, random output. The computation is incoherent and useless. The computational physicist's mantra is about guiding the search. If coherence breaks, we stop. If coherence returns, we continue. If the system becomes noisy or chaotic, loses coherence, we halt, reinitialize, and perhaps adjust parameters, like effective temperature, to help it escape local traps and continue its search for a deeper coherence. Core mechanisms: embedding, simulation, and benchmarking. We have three broad paradigms for Phi computation. 1. Analog Hamiltonian simulation, the Ising machine, and friends. This is the most direct. We build a system whose Hamiltonian, energy function, matches our problem. The Ising model mapping. Many optimization problems, max cut, traveling salesman, protein folding, can be mapped to finding the ground state of an Ising model. Minimize H equals minus sigma Jij Si Sj, where Si equals plus or minus 1 are spins. We build a physical system of coupled bistable elements. Physical implementations. Coherent Ising machines, optical. Coupled laser pulses, where phase 0 degrees or 180 degrees represents spin plus or minus 1. The coupling is implemented through optical feedback. Hezbollah oscillator-based Ising machines. Coupled electronic or mechanical oscillators that sync in phase or antiphase. Hezbollah quantum annealers, for example D-Wave. Superconducting flux qubits with programmable couplings, leveraging quantum tunneling to escape local minima. The computation. We let the system relax. It settles into a spin configuration that minimizes H. That configuration is our answer. 2. Topological quantum computation, computation by braiding. This is more revolutionary. Here, information is stored in the topological charge of non-abelian anyons, exotic quasi-particles. Computation is performed by braiding these anyons around each other in spacetime. The world lines of the anyons form a braid, and the quantum state evolves according to the topological properties of that braid, which is inherently resistant to local noise. The result is read out by fusing anyons and observing their output charges. This is computation as not tying, protected by topology. 3. General analog computing with Phi fields. We can use any controllable Phi system, like the wave tank or coupled pendulum simulators from 10.4.5, to solve differential equations or perform signal processing by literally letting the waves propagate and interfere. An optical field passing through a specially designed faceplate can perform a Fourier transform instantly, at the speed of light. The coherence criterion, exploratory coherence. Our coherence criterion for successful computation is specific. The computation relies on coherent exploration of a solution landscape. For classical analog systems, this means the dynamics must be sufficiently deterministic and noise-resistant to settle into a meaningful low-energy state. For quantum variants, it means maintaining quantum coherence throughout the algorithm's duration. The qubits must remain in superposition and entangled without decohering. If coherence is lost mid-computation in a quantum system, the answer is random noise. If an analog system is too noisy, it jitters endlessly and never settles. The dissonance indicator, premature trapping or decoherence. The primary dissonance indicators are premature trapping in local minima and decoherence. Local minima trapping, analog. The system settles quickly, but the solution is poor, far from the global optimum. This indicates the energy landscape is too rugged or the system lacks the kick, for example, thermal fluctuation, quantum tunneling, to escape shallow pits. The computation is incoherent with the true solution space. It found a locally consistent but globally poor pattern. Decoherence. The quantum state collapses to a random classical state before the algorithm completes. This turns a quantum search or simulation into a random guess. The signature is a loss of entanglement fidelity, or a failure to produce the interference patterns required for quantum speedup. Observing these means the computational run has failed. The system did not maintain the coherent search needed to find a good answer. The safety rail. Ruthless, problem-specific benchmarking. This is our most critical safety rail, guarding against hype and self-delusion. Any claimed computational advantage must be problem-specific and rigorously benchmarked. Define faster. Is it wall clock time? Energy consumed? Physical space required? We must specify. Benchmark against the best. Compare against the best-known classical or digital quantum algorithm running on the best available hardware. Not a strawman algorithm. Use known answer instances. For validation, test on problem instances where the optimal answer is known, through exhaustive search for small cases, or using a trusted difference solver. Full cost accounting. Include all overhead, cooling, programming time, readout time, error correction overhead for quantum systems. The safety rail rule. No claim of a computational advantage is accepted without a published, reproducible benchmark under these fair conditions. A Phi computer that is faster only by ignoring the hours of cryogenic cooldown time is not faster. A measurement scene, the coherentizing machine for MaxCut. Let's enact our roadmap's measurement scene. Scene. A network of 100 coupled lasers, a coherentizing machine, solving a MaxCut problem on a 100-node graph. The problem. A specific graph with a known optimal cut value, determined by a brute force software solver for verification. The mapping. Graph nodes, laser modes. Edge weights, coupling strengths in the optical feedback loop. The classical competitor. A high-performance CPU running a state-of-the-art heuristic algorithm, like a high-quality implementation of simulated annealing or a branch-and-bound solver. The pass. Demonstrated advantage. 1. Run the Phi computer. Let the laser system settle. Read the phase pattern. Decode to a cut. It finds a cut value within 1% of the known optimum. 2. Measure time. Wall clock time from problem loading to answer readout. 10 milliseconds. Hezbollah. 3. Run the classical solver. On the CPU, achieve the same solution quality within 1% of optimum. It takes 5 seconds. Hezbollah. 4. Result. The Phi computer is 500 times faster in wall clock time for this problem size and type. The advantage holds across a benchmark set of similar graphs. Pass. A genuine, measurable, problem-specific advantage. The fail. No advantage. The Phi computer settles quickly, but onto poor solutions, 10% away from optimum. The CPU solver finds better solutions in less time. Or, the Phi computer finds good solutions, but takes minutes to program and calibrate for each new graph, while the software solver takes seconds once the graph is in memory. The total time favors the software. Fail. The safety rail of benchmarking reveals no practical advantage. The Phi system might be a fascinating physics experiment, but not a useful computer for this task. The prediction spine, the hallmarks of a computational advantage. A true Phi computational advantage yields a clear prediction spine. 1. Scaling advantage. The scaling of resource cost, time, energy, with problem size, n, will follow a different and demonstrably better curve than the best known digital algorithm. For an Ising machine, perhaps time scales linearly with n for certain problem classes, where the best classical algorithm scales exponentially. This is the Holy Grail. 2. Analog speedup. An analog Phi computer, like the Ising machine, will find high-quality solutions to optimization problems faster in wall clock time than a CPU running simulated annealing for problems above a certain size threshold. Below the threshold, overhead dominates. Above it, the natural parallelism and continuous dynamics win. 3. Topological error correction. A topological quantum computer will demonstrate the key prediction. Logical qubits, protected by topology, will have lower error rates than the physical qubits they are built from. This will be shown by performing a known computation, like a small algorithm, and comparing the outcome fidelity with and without the topological code. Falsifiability, when physics is just a slow computer. Our falsifiability threads are the market forces of computation. Falsifier 1, the inferior solver. If a Phi-computer's solution is consistently worse in quality and or slower to obtain than a good heuristic algorithm running on a standard laptop, then it has no advantage. It is a slower, less accurate computer. The idea of using that particular Phi system for that problem class is falsified. If the overhead for error correction in a topological quantum computer, the number of physical qubits needed per logical qubit, the complexity of the braiding operations, outweighs the benefit of the topological protection, then it will not scale to useful large problems. The idea that topological protection is the path to scalable quantum computation would be challenged, though not necessarily falsified for all time. Material science might improve. These falsifiers ensure we are building tools, not curiosities. Tri-unity in natural computation. The computational process is beautifully triune. Time echo, the evolution. The computation unfolds in time. The relaxation of the lasers, the adiabatic evolution of the quantum annealer, the braiding of anyons. This is the duration of the thought. The problem is mapped into space, the connectivity of the laser network, the layout of qubits on a chip, the positions of anyons. This is the physical instantiation of the question. The system's motion through its configuration space, the flipping of spins, the tunneling through barriers, the winding of world lines, is the process of solving. It is the dynamic journey to an answer. A successful computation requires harmonizing all three: a spatial embedding that faithfully represents the problem, a temporal evolution that explores the space effectively, and a final motion that converges to a coherent solution. Lanterns across scales, letting the world think. The principle of outsourcing computation to physical dynamics is ancient. The brain itself is arguably a Phi computer. Neurons and synapses create complex, coupled dynamical systems. Thinking may be the process of this system relaxing into coherent attractor states that represent concepts, decisions, or memories. We are learning to read and maybe one day program this natural Phi computer. Middle scale. Ant colony optimization. An ant colony finding the shortest path to food is a swarm intelligence Phi computation. The Phi field is the pheromone concentration. Each ant is a simple actor, but the collective dynamics solves a complex optimization problem. We use digital simulations of this principle for routing and scheduling. A wild, speculative lantern. Could the universe's own laws be the result of a kind of cosmic computation, where coherent structures, like our patch of physics, are attractors in a vast landscape of possible laws? This is the domain of Book 10.9's Ultimate Horizons. The ethics of natural computation, truth in answering. The ethics of Phi computation is about truth in results and fairness in access. 1. Verifiable results. Because analog and quantum computers can be probabilistic or heuristic, we have an ethical duty to validate their answers where possible, especially when they guide high-stakes decisions, drug design, financial modeling, climate prediction. We must report solution quality estimates and confidence intervals, not just a single answer. 2. Fair access to advantage. If a Phi computer truly offers a massive speedup for breaking cryptographic codes or optimizing financial trades, it concentrates power. The ethical response is not to hide it, but to accelerate the development of post-quantum cryptography and to use the technology for public good problems, like protein folding for disease, in open, collaborative settings. 3. Environmental impact. A Phi computer that uses massive cryogenic systems may have a large carbon footprint. The advantage must be weighed against this cost. The ethic is to optimize for total computational benefit per unit of environmental impact. The power to let reality compute brings the duty to ensure it computes truthfully, and that its gifts are used to elevate all, not just to outcompete. The recognition skill, seeing the computer in the physics. You know you need this skill when you see a physical system that naturally minimizes something or finds stable patterns, and you have a problem that looks like a minimization or pattern finding problem. A magnet settling into domains to minimize magnetic energy. A chemical reaction finding the pathway of least action. A fluid forming vortices to minimize shear stress. A crowd flowing through doors to minimize personal effort. The moment you think, my optimization problem is mathematically similar to what that system is doing naturally, you're thinking like a computational physicist. The next step is the hard work of mapping. How do I make my graph look like its energy landscape? The master tree location. This part, 10.5.3, is a peak of synthesis in book 10.5. It depends on 10.3.1, 10.3.2, programming and control, to set up the system, and on 10.4.0, 10.4.3, foundries and topological engineering, to provide the physical platforms, laser arrays, qubit arrays, anyone systems. It is the culmination of using Phi systems for active information processing. It enables the next evolution, AI co-engineer 10.5.5, where we build systems that can themselves design such mappings and discover new computational uses for physical systems. It also forces us to develop economic valuation of computation 10.7.1. How do we price a millisecond of laser time that solves a problem a CPU would take hours to tackle? Return to the Phi. Let us zoom out. Phi computation is the act of posing a question in the form of a Phi landscape, and then listening as the universal tendency toward coherence whispers an answer. We are not imposing an alien logic, Boolean algebra, onto matter. We are asking matter to use its own native logic, the logic of energy minimization, of topological conservation, of wave interference, to solve a problem that we have translated into its mother tongue. The computer is not separate from the physics. It is the physics, purposefully engaged. We are learning to have conversations with reality where we ask not, what are you, but what would you be if, and then interpret its response. Zenodo and the equations of the landscape. If you want to see the full mathematical derivations and exact equations behind this idea, you can search for Holophase on Zenodo. There, you will find the scientific papers that this audio journey is built on. The papers detail the theory of adiabatic quantum computation, the mapping of NP-hard problems to Ising spin glasses, the performance benchmarks of coherent Ising machines against classical solvers, the theory of non-abelian anyons and topological quantum gates, and the rigorous error threshold theorems for topological codes. They provide the mathematical backbone that supports the dream of letting reality compute. So, picture yourself back in the computational foundry. The benchmark is complete. The graph on the screen shows two curves. One for the classical solver, rising steeply with problem size. One for the Phi computer, a shallow, almost flat line. They cross at n equals 50. For larger problems, the physics engine wins, decisively. You have just demonstrated that for a specific, useful class of puzzles, a box of lasers can outthink a supercomputer. You have let reality compute. This is part 10.5.3. Phi computation, letting reality compute. It is the moment we move from using computers to understand nature to using nature as a computer. In our next session, we will connect these powerful specialized computers. We move to Phi networking and protocols, 10.5.4. We will learn to link foundries, memory vaults, and computational engines into a resilient, planet-spanning, and someday beyond, information ecosystem. We will learn the protocols that allow Phi systems to talk to each other, share work, and form a coherent whole greater than the sum of their parts. We will build the nervous system of a Phi-literate civilization. Remember, one field, Phi, with its infinite echoes. We have learned to make its echoes speak, remember, and think. Now, we will teach them to join hands. Salam, and peace be upon you.